All right, so let's look at this. We're going to kind of graph this reaction in terms of energy. And remember that higher energy is equal to being less stable. Right, so the lower the energy of our intermediate or our product is, the lower in this graph it's going to be. And then this way, we're going to have something that's kind of like time, but really it's just reaction progress, because reactions don't necessarily go forward in time. Sometimes they reverse. So we start from the same starting materials. We have our conjugated system over here. That's going to be, we're going to arbitrarily kind of put this at this energy level right here. And then, depending on how we draw a resonance structure, we're going to have two possible intermediates, right? We're going to have our secondary cation, or we're going to have our primary cation, which is going to be higher in energy. And so we talked about this in the previous slide, right? We have two possible intermediates. We have a more stable intermediate, the secondary cation. We have a less stable intermediate, the primary one. And then our products, we have two products, and one is going to be more stable than the other. And so we have the more stable one is going to be the one with the alkene connected to more carbons. So that's the 1-bromo-2-butene. And then the less stable one is going to be the one where we have the alkene connected to fewer carbons. And that's going to be this one here, the 3-bromo-1-butene. All right, so we have plotted all of our intermediates and stuff. Now we just need to connect them. I'm going to connect them using different colors. So let's go with the more stable intermediate. So as the reaction progresses, right, we're gonna go get an H plus, and as that bond is forming, we go through a high energy transition state, and then we come back down to the this thing here, right, the carbocation. And then as the bromine comes in to attach that carbocation, there's not a whole lot of energy that we need to make that happen because the carbocation is so reactive. So that hump doesn't go up very much, but then we go down to this product, right? The secondary carbocation leads to the secondary bromide. Now, we could also start here and go to the primary carbocation. And now that's going to take a little bit more energy because we have to make a higher energy intermediate. But once we make this, right, this energy is going to fall off. We're going to go all the way down to the more stable product. The higher energy intermediate leads to the more stable product. So we have kind of two paths. We have the blue path and the green path in this reaction. And so let's think about what conditions we would need to kind of favor one of these over the other. If we want to make this more stable product in the end, that's fine, right? What we want is we want enough energy that all pathways are possible, right? So to make the more stable product, right? This is one where if you put in a whole bunch of energy, if we have enough energy to go through any pathway we want, we will kind of always choose the pathway that leads to the most stable product, right? Or not always, but eventually as time goes on, right, we'll kind of bounce back and forth between starting material and intermediate and products. And as time goes on, more and more things will kind of fall to this lowest point, right? The most stable point, the least reactive point, this final more stable product. So to make the more stable product, we need more energy, right? The more energy we have, the more all the pathways are possible. To make all pathways possible, and favor the most stable outcome. Right? So basically we need enough energy to follow this green path, right? If we can't get enough energy to get up to this unstable intermediate, we're never going to be able to get to the most stable product. So the more energy we have, the better to make the more stable product. We call this the thermodynamic pathway, right? So more energy is the thermodynamic pathway. That is the green path on the reaction coordinate diagram. Thermodynamic pathway. And when I say more energy, of course, I mean higher temperatures, right? The energy that we usually add to organic reactions is heat. So the higher the heat is, right, the more we're going to favor the thermodynamic pathway. So generally, when we say higher temperatures, what we mean is things above, 30 degrees Celsius. Room temperature is about 25 degrees Celsius. So if we add heat to something, usually that means we're going to start favoring the thermodynamic pathway. Now that changes for a variety of reactions. Sometimes the thermodynamic pathway is the one that's dominant at room temperature. Sometimes the thermodynamic pathway is dominant even at 0 degrees Celsius. It just depends on what your energy levels are for your intermediates. So we're giving an example here. In general, for additions of HBr and those kinds of things, we're looking at things that you heat up, right? So things like 30 degrees Celsius. But that's not true for every reaction. We have to kind of always remember that. So the thermodynamic pathway is a higher temperature above 30 degrees. When we have a higher temperature, we can access any pathway we want, and so we choose the one that leads to the most stable intermediate. Now, so then can we choose to get to the less stable product, right? How do we make, oops, I'm still green. How do we make the product that is not the most stable product? That seems like a much harder thing to do. To make the less stable product. All right, to make the less stable product, we have to go through the low energy intermediate, right? And so if we have enough energy to go through the blue pathway, but not enough to go through the green, we would obviously only go through the blue pathway, and we would only lead to the less stable product. And so to make the less stable product, we need less energy. We need only enough energy to go through the more stable intermediate. Right. So if we have less energy, we can only access the blue pathway. We only access the secondary cation, and therefore the secondary bromide as the product. And so in this case, that would be something where we would be looking at lower temperatures, right? So if we put less energy into the reaction, we're going to get, it's going to be less likely that we follow the green pathway, and so the thermodynamic pathway will no longer be available to us. Instead, we call this the kinetic pathway. These are usually operative at lower temperatures. And when I say lower temperatures, I usually mean 0 degrees Celsius or below. Okay. Now, again, same caveat applies. It depends on the reaction. Sometimes you'll get the kinetic pathway only if you cool things down to like minus 80 degrees. Sometimes you get the kinetic pathway even at room temperature. So each reaction is going to be different. You're going to have to be careful. But in general, the lower temperature will lead to the kinetic pathway, which means we go through the lower energy intermediate. Right? So we've got two new terms, and I want to write those on their own separate slide here before we wrap up. So I'm going to do that. So we have the thermodynamic pathway, or the thermodynamic product of a reaction, right? The thermodynamic product of the reaction is the product that dominates when the reaction is run at high temperatures. It is the most stable product. And when we're talking about conjugated systems and doing addition reactions like the one that we just did, right, that means this is the alkene attached to the most carbons. The other option we have is the kinetic product. The kinetic product is the product that results at low temperature. Right? When the reaction is run at low temperature, the kinetic product goes through the most stable intermediate, usually a carbocation, right? So most stable carbocation. So when we do this analysis, when we're looking at, well, is the reaction run at high temperature or low temperature, and we say, okay, it's run at low temperature, that means the kinetic product is going to be favored, then we have to figure out what are the options for the carbocation and which one of those carbocations is more stable. If you decide it's run under kinetic conditions, then you have to figure out what the two carbocations are and which one is more stable, because that's the one that's going to lead to your product. If you are running at high temperature conditions, and you need to figure out the thermodynamic product, then you're comparing your products and seeing which one of those is more stable. Okay? So next I'm going to do an example of this just to kind of walk through like what is the analysis that we can do, and that will help us, I think, kind of figure out where the what the difference is between these two things. All of that.